Welcome back to the deep dive. We've pulled together a really incredible set of documents today. We're getting a deep dive into the actual blueprints used to design and build 4 distinct, very complex modern enterprise platforms.
Yeah, that's the key
We're
here.
getting a genuine, behind-the-scenes look at how some of the biggest technical challenges are actually solved in the cloud.
That's right. We're not just looking at the finished products. We have sources covering an AI-powered video tutorial platform, a high-volume IoT administration system, a really specialized fleet management platform, and, and this is a cool one, a critical developer tool called the AI Prompt Generation Architect.
So our mission today is to extract the technical DNA of these systems.
Hmm.
We want to move past all the marketing language and really understand the common design philosophies.
The foundational choices.
Exactly. Choices about scalability, event handling, security. I mean, the things that define success in modern software architecture.
And what immediately jumps out from all this material is the emphasis on planning. One of the blueprints talks explicitly about the need to build an imaginary yet technically accurate model before you even write one line of code.
Right.
It just reinforces that idea that architecture isn't about the code itself. It's about defining the system's behavior and how all the pieces connect first. So we're basically reverse engineering those foundational stories for you.
Okay, let's unpack this then, starting with the AI-powered video tutorial portal. This is a comprehensive content and learning platform, and it uses a full microservices architecture. So for a system that's all about managing and serving content, why take on that complexity? Why break it up into all these independent services?
Because content management and delivery they're rarely one single task, You have video streaming, user authentication, searchable metadata, automated content
Just
enrichment,
competing for the same resources.
all competing. And microservices let you treat the video stream, which demands really high asynchronous I/O, completely differently from, say, the database integrity checks. Each service can scale on its own based on its specific load, which keeps the whole system responsive.
And within that approach, the architecture immediately shows the efficiency of a polyglot stack. So they aren't just using one language for everything.
No, it's a textbook case of using the right tool for the job. For the core data layer and, the standard RESTful CRO operations connecting to MongoDB, they chose a super reliable Node.js and Express API service.
Okay, fast and efficient for basic stuff.
Exactly. But then they brought in Python for the more advanced features.
So what makes Python necessary here? What's it doing?
So Python, and specifically using FastAPI, that's handling the computationally heavier tasks. That service is responsible for the comprehensive search capabilities, which, that often requires complex text indexing and parsing. It also handles the secure advanced authentication, like OpenID Connect and Google Oath.
And the sources mentioned a really critical enterprise pattern here. E-tag-based optimistic concurrency control. That sounds pretty technical, but why is that so essential for a platform's integrity?
It's all about preventing data corruption. I mean, if you have 2 users trying to update the same record at the same time, simple locking can cause huge delays.
Right.
Optimistic concurrency lets both updates proceed, but it checks a version token, that's the E tag, before it commits. If that E tag has changed since the user loaded the data, the update gets rejected. It ensures data integrity and high throughput without forcing these unnecessary delays on people.
And that's critical when you might have a bunch of people editing course details at once.
Absolutely. That attention to detail is really what defines enterprise architecture.
Okay, so moving on to the actual delivery-serving video files at scale, what stack choice did they make for the content server itself?
They chose a highly specialized, really lightweight server called the Courses Portal Content Server. It uses Fastify again, built on Node.js because it's so high performance and asynchronous, which is perfect for streaming. But what's really interesting is how they manage the source files. They use a utility called UnionFS.
UnionFS, can you clarify that for us? I mean, why not just use one big centralized file storage?
UnionFS solves a massive content organization problem. It lets the server aggregate video files from multiple totally separate source folders, maybe some are stored locally, some on network shares, and it presents them to the application as if they were all in one single unified file system.
Ah, so it gives content managers enormous flexibility. They can organize and update source material without breaking the delivery mechanism.
Precisely.
That makes perfect sense. Okay, now let's talk about the AI part. The source material refers to intelligent agents that handle the automated enrichment.
Right, there are two workhorses here. First is the automated metadata enrichment agent. It uses Node.js and the Cheerio library. Cheerio is basically a tool for efficiently navigating and parsing HTML. This agent scrapes external course sites for descriptions, for images, and it intelligently updates the MongoDB records to keep the whole course catalog fresh.
So it's automating the job of a research assistant.
Exactly that. And the second one is the Course Content Scanner and Metadata Processor, which is a Python CLI tool. It recursively scans new folder structures, it extracts technical metadata right from the video files, and it processes supplementary text like SRT subtitles. Python is just excellent for that kind of file system and heavy data processing.
So if we look at this stack, you have Node for serving and scraping, Python for the advanced APIs, and heavy processing. It's a clear choice based on computational strengths, and it's all containerized with Docker. But doesn't maintaining a polyglot stack like that introduce, a massive amount of overhead and complexity?
That's the core trade-off. It absolutely increases operational complexity. You need engineers who are proficient in both environments. You need robust CI/CD pipelines. However, the performance and specialization gains, they often outweigh that complexity cost, especially when you can tailor the resource consumption so precisely for each microservice. You get an efficiency that, frankly, a single monolithic stack just can't offer at this scale.
That gives us a great foundation for understanding architectural specialization. Let's shift gears from content delivery to high-volume, real-time data ingestion and processing. We need to talk about event-driven scale, which brings us to the Acme IoT Administration System. This was designed as a pure blueprint, focused on resilience. What were the mandated architectural goals?
Resilience and throughput. Those were key. The goals were to be scalable, observable, event-driven, secure, and fully cloud-native. I mean, they were planning for millions of income and telemetry events per hour.
In a system generating that much data, the data strategy must be hyper-specific. How do they separate the transactional data from the analytical data?
They enforced a dual data pattern right from the start. They use Cosmos DB, a globally distributed database, solely for primary transactional data and the current state of devices, things like serial numbers, firmware versions. But for the actual analysis, the where was this device last week kind of questions, they chose time series insights.
Okay, why is time series insights so crucial here?
TSI is purpose-built for high-volume ordered timestamp data, which is exactly what IoT devices generate. It allows for incredibly fast, efficient querying and aggregation over time windows that a standard relational or even a document database would just choke on. The system uses a dual write pattern where worker services send telemetry data to both databases at the same time.
That dual write pattern. It sounds elegant for optimization, but it also raises a big architectural question. Doesn't writing to two separate databases simultaneously create potential data consistency issues if one of those services fails mid-write?
That's a valid, critical question, and that's precisely why the whole architecture relies so heavily on asynchronous event processing using the service bus. The API itself is very thin. It just accepts the initial command.
Hook.
That command becomes an event. Producers publish the event, the service bus carries it reliably, and workers consume it. If a worker fails trying to do that dual write, the event just stays in the service bus queue, ready for reprocessing until it's successful. That decoupling is the mechanism for guaranteed delivery and resilience.
So the event layer is what handles the responsibility and integrity of the whole process. It prevents the API from ever becoming a bottleneck.
Exactly. And the final layer of protection here is security. Dealing with physical, connected assets, that requires robust enterprise security. The blueprint demanded Azure AD for API authentication, Key Vault for securely storing secrets, and critically managed identities.
Managed identities. That's another one of those technical terms we hear a lot. What problem does it fundamentally solve for an enterprise?
It eliminates the single greatest security risk, secrets leakage. Instead of hard-coding database passwords or API keys into config files, which could get accidentally checked into source control.
Which happens.
It happens all the time. Managed identities provides an identity for the service itself. The service uses its own identity to authenticate with other Azure resources, like Key Vault or Cosmos DB, without ever handling the actual secret token. It dramatically simplifies credential management while massively increasing your security posture.
That's a powerful pattern. Now, let's see how these principles translate to vehicle telemetry with the VxCare fleet management platform. How does this platform handle that need for instant real-time updates?
So VxCare monitors real-time vehicle status, driver behavior, predictive maintenance. It's built on the .NET 9.0 ASP.NET Core stack and also uses MongoDB. But where Acme IoT leaned into asynchronous guaranteed delivery with Service Bus, VxCare prioritizes immediate user feedback using SignalR.
SignalR for those dashboards that update instantly, right?
Yes. SignalR manages persistent bidirectional communication. It's essentially sophisticated WebSockets to stream immediate telemetry data, alerts, and notifications directly to the browser or a mobile app. This is how they get that live driver behavior scoring system and instant geofencing alerts.
So we've got a clear difference in focus. Acme prioritizes eventual consistency and resilience using queues, while VxCare prioritizes the immediate delivery of data to the human user with SignalR.
That's the crucial distinction. And VxCare's architecture is also designed to be microservices ready and really flexible. It supports integration with all sorts of event providers, Azure Event Grid, AWS Event Bridge, Kafka, making it very cloud agnostic in its event flow.
Yeah.
It's designed for high scalability and has built-in multi-tenant support.
Okay, so we spend a lot of time on these massive scalable platforms. But the complexity of building, deploying, and especially interacting with these systems, particularly when AI gets involved, requires specialized tooling. That brings us to the AI prompt architect. This isn't a huge platform, it's a developer tool. What's the major problem this thing solves for developers and prompt engineers today?
It solves the efficiency and accuracy problem of context generation. As we build AI features into these platforms, the prompts we send to large language models have to be precise. If you want the AI to analyze an architecture blueprint or debug some code, you need to feed it all the necessary file contents, the folder structures, and specific requirements without hitting token limits or, just introducing noise.
And doing that, manually copy and pasting code, documenting the file hierarchy, it's so tedious and it's expensive. Every extra token costs money.
Precisely. This tool is an optimization layer. It's designed to cut cost and improve the quality of the output. It's a browser-based app built simply with a Node.js Express and a vanilla JavaScript, but it's designed to feel like a desktop IDE. It has a vcode-like folder tree interface, letting users navigate their local project directories.
And how does it translate those files into a usable prompt?
The user selects the relevant files and directories, and the tool automatically generates this organized, markdown-ready context. This output includes the full folder structure and the contents of the selected files, which ensures the AI model gets a really clean, structured view of the project.
So it's synthesizing the environment that's needed. What about the human input, the actual prompt itself?
It wisely separates the context from the instruction. It gives you dedicated, structured panels for the human input. The specific role you assign the AI, like Senior Node.js Architect, the task, like identify the SQL injection vulnerability, and the functional requirements. This structuring makes the prompt unambiguous and highly effective.
That segmentation seems absolutely vital for getting high-quality AI output. But what about utility features for the developer workflow?
Well, for iteration and collaboration, it offers persistent state saving in a JSON format, so you don't lose your finely tuned context selections. And critically, it has a ZIP export feature that packages the entire context, the selected files, and folder structure. This makes it super easy to share precise context with colleagues or just archive successful prompts.
The AI prompt architect is such a clear example of how modern architecture now extends beyond just APIs and databases. It includes the critical tooling you need to optimize your interaction with this expensive, complex LLM infrastructure.
Absolutely. The tools that shape and manage the context we feed into AI are becoming architecturally essential. They sit right there next to the event bus and the core services.
We've synthesized a huge amount of technical detail here across the video portal, Acme IoT, VxCare, and the prompt architect. Let's try to bring this to a close by identifying the common denominators, the threads woven through all these blueprints.
The synthesis is powerful. Despite their diverse purposes, all these platforms share a commitment to key standards. First, containerization Docker and Kubernetes is universal. It's for deployment consistency and scaling. Second, robust, standardized authentication is just non-negotiable. We see JWT tokens, Google OAuth 2.0, and enterprise identity integration using things like Azure AD.
And the third common denominator seems to be that comprehensive focus on observability, sort of the defensive layer, for these complex distributed systems.
It's everywhere. They all mandate comprehensive monitoring, including dedicated health and ready endpoints, and structured logging using tools like Serilog for .NET systems. And structured logging means the logs are machine-readable JSON, not plain text, which is essential for quickly debugging an issue across dozens of microservices at once.
And looking at the roadmaps for both the Learning Portal and the fleet management system, AI isn't a future possibility, is it? It's a fundamental trajectory.
That's the biggest takeaway. Both platforms are investing heavily in advanced AI-powered features. For the Learning Portal, that means personalization, automated transcript summarization, maybe generating custom quizzes. For VxCare, it means predictive maintenance and real-time route optimization based on current traffic and vehicle load.
Which brings us right back to the blueprint. We've seen that strong architectures define a system's behavior before any code gets written. If every major function in these systems will soon be handled by predictive or generative AI, how fundamentally will these features transform the basic architectural requirements?
It raises a really profound question. Is planning for intelligence now the new core challenge of modern system architecture? We have historically optimized data flow for transaction throughput for read-write speed. But if the core value shifts to AI, does the blueprint need to prioritize low-latency model serving, feature stores, and versioning of massive training datasets over traditional CRUDI optimization? The architectural priority shifts from handling transactions efficiently to ensuring the AI model is trained, served, and continuously updated with the highest possible data quality. That is the next great architectural challenge for everyone building these systems.